Yeah. And so in this topic, you're going to show you some really basic information or introduction to electrical motor system. I forgot to turn on my camera. Yeah. Then in here, you can firstly understand a bit some basic information about motors. And also we started with some inductor. So that from inductor, then we construct the inductor into a motor. Probably will be some static and also dynamic motor system. We also try to discuss some future aspect for motor system. So first of all, I'd like to ask you a few questions about how your knowledge in the electrical machine, right? So firstly, what do you think about the meaning for electrical machine? And Shito, could you tell me what it is? How is that the title for the course, right?
Maybe the electrical machine is a type of tool to transport the electricity to mechanical energy.
Okay, yeah. So by definition, motor must be something like this, electrical to mechanical. But machine, this term actually include a few more than that. Maybe generator from mechanical back to electrical. Some of them may be a static, don't have any mechanical output or input, like transformer. You see, transformer is also can be classified as a really basic machine. So that's why if you see most of textbook or website, the first chapter they learn electrical machine will be transformer. So that means transformer could be a really basic machine. You can start to understand more about it. And then we're also looking into what kind of motor. It is like what's the first motor in the world, in the invention, that's something you look into. Basic machine like DC motor is first basic machine we need to understand it. So many of the textbook or whatever courses we have, we firstly try to understand more about the basic motor system, which is DC motor. Why is that? Because I think we firstly invent the motor with the DC motor. That's how we started from there. And then most importantly will be people will start to look into the difference between DC motor and AC motor. Right? And Ali, could you tell me what's the difference between AC and DC motor?
First thing, in AC, like it's alternating current, it's keep changing. And but in DC, it's unidirectional, it's not keep changing. And also in DC, we use like brushes, and in AC, legs or these like brushes.
Yeah, that's very good explanation. And in more detail, when we study more detail about the course, we investigate more detailed difference between AC motor and DC motor. Basically, it would be the power input. Then next, we try to examine about the efficiency for motor. For instance, how when a motor used in different application, like EV, electric vehicle, maybe industrial drive, what do you expecting the efficiency it should be? And then we go through a few examples for electrical machines. Can you tell me some typical example for electrical motor system? Anybody can tell me? Many of them, right? Many examples. Like, could you tell me a few examples of electrical machine we can use?
One of those could be the air conditioners. And generators. No, the generators are something else.
Yeah, generator is also a good electrical machine system. Yeah. Okay. So that's basically the initial thinking for electrical motor system, right? So the content for this course, including this number of topics, some introduction, which firstly to some revision for inductor. And then we just investigate about the efficiency for a motor. And then we start to look into how is the invention like for motor. And then we try to examine about the difference between motor, electrical machine motor, against the engine, gasoline engine. So, and then that had been really big competition in the history of the motion system. We're looking into the application, and then we also talk about different types of the motors, so many types now. And then having said that, then we see that there's a air gap phenomenon in motor transformer and maybe inductor. So we try to understand some mathematics for this kind of the air gaps phenomenon. And then we try to conclude the work, and then we have some final conclusion remark. So first slide, we'll be looking into the transformer, motor, and generator. These are three major components for electrical machine. Like transformer is a so-called static machine without any moving part. And then we able to control the input and output. I think we all know about transformer. I think we look at more detail, we find that transformer, we can able for as conversion from electrical energy like the voltage to voltage, current to current, and they have same kind of power between input and output, but they do not change the frequencies. So input frequency, say 60 Hertz, output will be 60 Hertz. So that's the basic operation for transformer, so-called static transformer. And the motor, obviously, we try to convert the electrical energy into mechanical, so the basic operation. And then having said that, a motor can be rotational or linear. Basic motor you learn every day will be rotational, but we do have so many linear motor. In the future, we also have 3D motor, 3D rotation or maneuver. And that will be really important if you want to construct an electric vehicle or maybe robot. We do need to understand how the operation of a linear motor like. Because in a robot, we don't only use rotational motor, we use linear motor, maybe 3D motor, which has been ignored at the moment. You see many robotic experts, they say they're expert, but they only focus on control, but they haven't understand too much about the motion system. Like what kind of motor will be available, what kind of generator will be available, how to charge up the robot. So without this information, they cannot design a good robot. They only based on rotational machine and probably DC motor, but they don't know there's so many motors available. So in this course, I will show you all the different type of the motor will be available. So you can see that those good motor for a good robot or good electric vehicle. So, but basically you can see that we divide the motor into AC motor and DC motor, as you can see in here. And then we can able to program different kind of the input voltage to the motor. So other motor also important, including the switch reluctance motor, stepper motor, that will also widely available nowadays. Stepper motor, I think anybody in the high school, when you've done any project, maybe in the undergraduate, you also come across with the stepper motor too. So that's also simple motor we have been using. And then we also have a generator, which we convert mechanical energy into electrical, which is also quite interesting. And then, of course, AC generator for the AC, we also DC generator, so-called dynamo, which are able to produce some kind of DC current as well. So that's how we define different type of the motor system. So all the thing will be in my lecture notes. I think you go to the canvas, you can see all the material or upload them in the different module. I divide my module into week 1, week 2, and week 4, whatever. Much easier for you to look into them. So now that here is some more information about transformer, which usually convert the voltage or current from one level to another level. It can be step up or step down. And then you can also see that current transformer is really famous conversion system, because if you want to convert the current, like when we want to do the current measurement for high power, low power, we do need to convert the current with the another format so that we're able to do the measurement. For instance, our power plant system, you may have 1,000 amp. We do not measure our 1,000 current. It's too expensive to do that. And then we have a single loop pass through the high current. And then on the other side, we got multiple turn. You can convert this high current into a really small amount of current then to conduct the measurement. And then transformer can also help us with the isolation, because in many cases, electrical conduction can be really dangerous. So we don't want to touch any high voltage, high current in the power system or EV system or robot system. So we do need to provide the galvanic isolation, which magnetic barrier to understand the current. And from motor as well, we have the rotational motor, linear motor. There's the two basic motor we're going to learn. We also have industrial drive system, and then we apply them for electric mobility, electric vehicle, and of course, robot and generator are really big topic. As I mentioned many times, today everybody has at least 1 to 2 cell phones. For next 5, 10 to 20 years, everybody should have your own robot to work with you. So of course, today we don't have that many robots, but I think the next 20 years, robot will be such a common devices. Everybody should have one. So you can see that that's how the evolution for a robotic system. So robot do need a motor. Without motor, robot is not working at all. And of course, another big topic will be electric vehicle. Today, for the whole United States, we got 8% of the vehicle are electric. And then we know that in the next 10 years, you go up to at least 40%. And next 20 years will be 80%. All the vehicle in the United States or in the whole world will be converted into all electric vehicle. So that is the demand now. So we need to know how to design the motor, how to design a generator, how to design the moving part. And having said that, the traction motor, the main motor in an electric vehicle is, of course, must be important. But in all the automotive system, any vehicle, there will be at least 50 motor there, small motor to control the wiper, control the door, control many different kind of moving parts. So many new vehicle, there will be hundreds motor. So that's why motion control will be really important for electric vehicle. So and then, what do we need then to drive motor? We need some power electronic to control them. For DC motor, we need some power electronic to control the DC. For AC motor, we control the AC voltage. We need to vary the voltage applied to the motor. We control the current and control the frequency. Because the rotational speed for a motor is related to the input frequencies. So in this case, we do need to control the frequencies. Our power point there will be 60 Hertz. So the nominal frequency for rotational for motor will be something like 3,600 RPM. But however, when we want to vary the speed, of course, we need to control the motor speed. Then we need to adjust the input frequency to the motor driving system. And we are not using 60 Hertz, we are using many other frequencies. So that's to say the really simple motion control system is so-called voltage control chopper. We chop the voltage, chop the input waveform to the motor to control the operation. And then this method, we call it pulse width modulation, PWM. I think this term is really famous term we use for all the motor control system. So the key component for motor, obviously, it must be the winding, the motor winding. And then those windings can be connected in many different ways, including the star connection, and then delta connection as well. So that's one of the typical connection method, but of course, there will be many other methods. Like we do have a lot of separate winding to form the primary and secondary. And then we also, the transformer, or as I mentioned, can be considered as a very simple machine, but this machine will be stationary without any moving part. So all the motor winding, machine winding, will be winded on the magnetic core. So in this case, why we do that? Because we need to increase the magnetization to produce some kind of the energy storage. So here will be one typical example how we connect the motor in the vehicle. Really typical simple diagram to do that. So for electric machine, the motor here, we connect with some gear to the electric vehicle shaft. And then for motor, we do need some control electronic, so-called the motor drive to drive the motor. And then we have some control electronic to do that. So that's basically how a motor related to a EV system. The good thing in here, you can see that this motor are doing two jobs. One is the motoring, one is power regeneration. So that means the generator and motor actually can be implemented together into a motor system. Like an EV, of course, we need to have power regeneration. regen anyway. In the vehicle going down the hill or braking, we return the dynamic energy back into the motor system to the battery. So that's how typical application for motor. But our motor will be mainly constructed by the inductor. So that's why first thing we learn will be inductor. I think you all learn about inductor. I'm not quite sure the gentleman in the middle, though you also learn inductor, right? Yeah. So inductor, what's an inductor? And anybody can tell me what's the meaning of inductor? Shitao, can you tell me the meaning?
Inductor is a energy storage using the current engine.
Right. Okay. Then we also learn a number of basic equations for inductor, like L di dt equal to voltage, right? That's inductor. We also learn some basic inductance equation. L is proportional to number of turns squared, right? That's the basic equation we learn. And then we also learn about the flux linkage, how to use number of turns to link more magnetic flux. So that's also we learn about terminology for flux linkage. And then we also, basically, inductor can be air core without any magnetic core inside. We can also with a magnetic core. The magnetic core usually can help us to increase the permeability so that we have higher inductance per unit number of turns. So when number of turns increase, you can see here, the inductance basically increase in a ratio that would proportional to number of turns n squared. So the magnetic core, of course, mainly controlled by the permeability mu. I think that's a really common terminology. We use mu law or mu R, this terminology. So the relative permeability, mu R, I think you also know the term, right? That will be vary between 1 to really high number. For pure atmosphere air will be 1. And then for iron core, usually will be a few thousand. Yeah. So that's a common mu R term we understand. So inductor basically helps to store the energy, and then the inductance will be usually measured in the unit of Henry L, but H, right? But this unit usually really large. So most of the inductor we use in the motor will be something more like mini Henry mH. And then for power electronic inductor we use sometimes can be as small as mu H micro Henry as well. So the core itself will be help us to do the winding, and for really small inductance, then we use air core. For some high magnetization with so-called the ferromagnetic core, that would mainly have iron core or maybe ferrite, it helps to increase the inductance. Each winding, they're copper winding, but their winding usually are laminated. They have a coating so that all the winding will not touch each other electrically. And then, but that winding will be something also a part of the design will be important. Because we usually increase number of winding to increase the inductance or increase the motor inductance. And then we can see the basic equation, we all know this kind of equation, L di dt equal to excitation voltage. And then the rate of change will be this, right? The energy storage will be this equation. So this equation also something we need to be noticed. So energy equal to half Li squared, that will be the energy stored in the inductor. And then we can see that the power operated by inductor or by motor would not only understood by the energy E, the power. Let me use a pen to see able to. The power will be equal to energy time multiplied by frequency of operation. It's really basic formulation, right? If you apply them for inductor, that will be Li squared. Yeah. So for motor or whatever we tend to use, it seems that if we want to fix power flow. Then when we increase the frequency, under the same power level, we can decrease the inductance. So that's a really important phenomenon for any motor or energy storage system. Same kind of power flow, for example, like 1 kilowatt, 10 kilowatt, 1 megawatt. Then if we want to ensure that the inductor size not to be too large, what we can do is operate the whole system using higher frequency. Like when we increase the frequency in this manner, we can decrease the inductance. So in this case, the size can become much smaller. So that's why a motor, if we want a motor to become smaller size, we use high-speed motor. For instance, a motor now we're using 60 hertz. If we excite the motor at 600 hertz, the motor size can be reduced by 10 times. So that's the phenomenon why we gradually move on to high-speed motor operation. For example, like in an electric vehicle, the motor inside are using high-speed motor. So in this case, we can reduce the motor power. Under the same power, we can increase the motor power density to be much smaller. So the motor, we can reduce the size by many times. So many of the EV today we are using, the motor operate at high speed, so we can reduce the size in this kind of reverse manner. On the frequency, yeah. So for example, like you go to a Tesla motor, the motor is so small, but they're 100 kilowatt. That's impossible, right? In the old day, when we have a 100 kilowatt motor, the motor is that big. But of course, impossible for EV. Such a big motor is too heavy for an electric vehicle. They like to reduce the overall size. By doing that, they shrink it to small, about that size. For EV motor, inside most of EVs, they are using high-speed motor. They are not using high frequency operation. They are not using 3,000 RPM, 30,000 RPM. That's the nominal speed. So that's how they do that, to reduce the size by many times, 10 times. Then we are able to do that. So that's the operation for the motor nowadays. We have some other control method. But however, when we have high speed rotation, that means the driving operation, the PWM driving frequency also need to be high speed as well. So that is come into the power electronics. The power electronic able to switch all the waveform, the PWM, much higher frequency. Before, perhaps 60 hertz, we can only drive them at maybe 10 kilohertz. It will be quite comfortable. But now then, we want to increase the rotational speed to 6,000, for instance. Then probably our PWM waveform, the driving electronic need to be much higher frequency. From 10K become 100K. And then come into computer chips to control that waveform, how to generate that control method. That will be much higher speed microprocessor. Then we need to use much high performance control system. So everything need to gradually move on to higher performance. Before we may only using MIL-P, but now we use DSP or FPGA or maybe even higher speed. Yeah. So that's the technology move on. So Here would be a basic equation for inductor. I think you see this kind of equation many times. So the basic equation B equal to mu H, this basic correlation between H field and the B field. B is the so-called magnetic flux density related to area. If the same kind of flux passes through a certain area, we can modify it by vary the area. And then another term is H field, magnetic field intensity. So these two are important terminology we use in magnetics. I think if you do understand something about that, right? Have you learned BH? Right, good. So the mu is the permeability is controlled by two parameters. One is the mu naught, which the mu naught is a natural constant, 4 pi times 10 to the minus 7. And the mu R is relative permeability related to the material we use. For instance, pure air will be 1. And then for ferrite, that would be, say, 3,000. For example, for some powder iron core, that can be 100, 200. Yeah, for some micro ferrite material, you can go up to 10,000. So nowadays, we tend to operate the mu R to be really high so that we can have higher performance for the permeability. And then the flux actually are given by this equation, mu Ni over L. That's a really typical equation. And then you can see that can also rewrite them into F over R. F is so-called the MMF, electromotive force. R is the reluctant. Just a quick revision. I think you learn all of this, but just a quick revision to remind you what we need to understand here. So MMF is also the driving force of magnetic circuitry. We can somehow relate them to electronic circuit. And the unit is called the ampere turn. Sometimes it's the Ni input to them. The basic inductance equation, that's a really famous equation, mu N squared over L and then A, right? So that's a typical equation. And then see that BH curve will be like that. That is a really typical BH characteristic. H highly related to the input H field. So when the current increasing or magnetization increasing, you can find that eventually the material getting to a something saturation, more flat here. And the mu R will getting more opposed to unity, 1. Of course, in the initial permeability here, the BH characteristic here, so-called initial permeability or the nominal permeability, that is the permeability for the material we use. For any material here, initial part will be more linear. But when we start to excite them with higher current, higher magnetization, then this curve will get more flat opposed to unity. I think you learn all this in the physics, right? Or electromagnetic course. But in UC Mass, we don't have the electromagnetic course yet in electrical engineering, but we'll soon have it next year. But these are some initial equation you can learn. And then we try to do some comparison. This is really famous comparison table in all the textbook. When you try to compare the magnetic circuitry with the electrical circuitry, the column in the middle, electrical circuit, basically is the Ohm's law. We know that. And then for magnetic circuitry, the driving force will be so-called MMF F. So this very famous term is mainly about Ni. Ni driving force, you can see the I is the current, N is the number of turns. So you want to include the driving force to an inductor, to a motor. Then firstly is the current. Second will be number of turns. If you don't have sufficient current, you got to put more number of turns. So that you increase our first linkage, linking the magnetic core. And the flow quantity is called the current. In the electrical side is the electrical current, but for magnetic is the magnetic flux, the phi here. So the unit is called Weber, just like all the magnetic flux flowing through the magnetic system. The opposition term, we call the resistance in the electronic circuitry, but in the magnetic circuitry, we call the reluctant. That's the term I mentioned just now, R term. The vector mainly highly relate to the dimension here, L and the A, and also the mu here. So that's why we build a simple relate to the Ohm's law, V over IR, but in here is the Hopkinson law, which is also very famous correlation. So in many cases, when we solve a magnetic circuitry, including motor, magnetic circuit, or transformer, we can actually model them by using reluctance. Any magnetic circuitry, we can write down the reluctance equation or parameter, and then work out how they work in parallel, series, and series parallel, like what we did in the electronic circuitry on the left-hand side. So this is very famous correlation. Everybody know about it, but just have a quick version so that you know what it is. And then for efficiency of machine, we also need to mention it to you. Today, the electrical machines are really, really high performance. For transformer itself, 99% is really common. We can very easy to make any transformer, 99%. Of course, if you come to my lab, come to my research, I show you how to make a transformer. We do have a project, because later I will talk to you about what is the project requirement in this course. We don't have a lab section, but we do have a project. We have a list of projects for you to choose from. Then some of them will be a transformer anyway. So typically, transformer efficiency nowadays, and you go to the power plant, go to the substation, or in those transformers we use in the adapter system, charging system, they are 99%. They're all 99%. Even though some really lousy transformer you buy will be 97 to 99%. And for motor, a good motor usually 95%. So those EV motor, 95% is the low. Maybe some of them even 96. So for industrial drive in the factory, assembly line, those motor making the system, they are 90% at least. And then for those low-cost motor, so-called the really average motor, RC motor, 80% could be. Then, because the efficiency of motor is not 100%, so a portion of energy will go to power losses. When we have power loss for any motor, we need to think about the thermal management. For instance, an electric vehicle, even though 95%, the power loss is still really high. Tesla motor can be 200 kilowatt, 300 kilowatt. Even though 5% loss, that could be something like 15 kilowatt, 20 kilowatt within a small region. You see, your hair dryer at home will be 1 to 2 kilowatt. But motor, so small size in a vehicle, it needs to have power loss for 20 kilowatt. So how do we remove the loss? If you don't remove the loss, what happens? Ali, what happens if you don't remove the loss for a motor?
It becomes costly.
The motor eventually melt. The winding, the copper winding will melt, short circuit. The coating, the copper wire, between them is an enamel coating. That coating only can last for 120 degrees C, at most 150. Any high temperature, they will melt, short circuit, punch through. And also magnetic material as well, at higher temperature, they will lose their magnetization. The mu R is not 3000, become 3. Then you lost the permeability. It becomes not a motor. You cannot transmit the power. So that's why the motor is really scared about the high temperature. So that's why all the electrical machines, like in EV, they got a cooling system, liquid cool, to remove the heat. If you don't do that, the motor is not working. So we have thermal management to deal with them. So the best performance of motor will be room temperature, 20, 25 degrees, the best. Anything beyond that is not very good. Beyond that temperature means higher or lower, also no good. Why lower temperature is also no good for the motor? Anybody can give me a hand? Servo, I think you know that. Why we don't like too low temperature for motor?
Low.
Yeah. Sorry, say again?
Increase the resistance.
Efficiency.
Decrease the current flow.
No, because we're too low temperature, the magnetic material is not really good. The dipole inside is not moving really well. The permeability also become affected. So that means don't think about low temperature is good for motor, not good either. And also the copper coating, at too low temperature, it crack. Some of them may not maintain its isolation properly, aging, crack. So you can see that if you put the coating inside the low temperature, minus 50 degrees, it probably is not working really well. Crack cannot last for long. So that's why thermal control is important. Your vehicle, your industrial drive, your vehicle putting in the freezing environment for too long is not working. The battery is not working, the motor is not working. So you do need a thermal control. Make sure it works. So your EV cannot put it outside for too long. Better to put inside the garage.
That's why the EVs can't go in the colder regions because from what I've seen, the Teslas or any other EV, they don't sell much in the cold regions, right?
That's right. They do a temperature range operation. So they do an internal heating or thermal control system. Make sure internal organ, internal component are maintained under their lifetime requirement. So then you put an EV there, they will consume some energy. That energy from battery is to maintain the basic nighttime operation. You could not only, having said that, the sensor, you can have off the sensor to save some energy, but something like the maintain mode, the vehicle must be there to maintain the basic operation of battery. Say the lithium-ion battery, you can't make it less than 20 degrees C, means the battery will die forever. So you don't maintain the battery. So there's many things we need to thermal control. The motor itself, of course, battery got more thermal control we need to look into, but motor, we also need to be careful. Too high, too low temperature is not good for motor either. If you buy any motor, the manufacturer tell you what's the operation temperature. Another parameter is the storage temperature. The storage temperature will be much wider than the operation, but we do have requirements for the storage. Any component, any equipment, we do have a storage temperature. Even though you buy a TV, your computer, there will be storage temperature. You can't put the computer anywhere because the thermal issue. So that's why for the cooling is important. We learn about the cooling for the motor system, including the forced cooling, forced air cooling, liquid cooling, also important. Some motor, of course, we can use electrical cooling, but those only low-cost motor. For high-performance motor, we do need to have a really strict requirement for liquid cooling or forced cooling. So now the history. The motor invented, of course, is quite a nice history we know. Of course, it's not except I just tell you about some history of development. At least as an engineer, you know about the history. In 1740, we started to look into the electrostatic principle to understand about the electrical magnetization. That's really basic information. We start to study electromagnetic, how a wire being moved. And then for 1820, and then we start to look into when a current passes through them, a wire, how it generates electromagnetic field. So that's the first interaction, how we understand electricity and electromagnetism. And 1820, the same time, the people, this gentleman, Ampere, I think is very famous then. All the current are named after him, right? Ampere is his scientist developed how the current relate to the force. That's one of the marvels. And then Faraday, 1821, he started develop electromagnetism, how he developed basic rotation. So that's why Faraday, of course, everybody know about him. Yeah? And then since then, Peter Barry developed the first simple machine like here, how you make the motor start to rotate. And then 1834, Thomas Davenport developed the first DC motor. And then he filed a patent for that. So US patent. The patent number is 132, which low number. Today, our US patent number 7, 8 digit. Is the first few people have a US patent. Number 132, low number. So you can see that there's a really first few invention in the US history. Interesting. And then Nikola Tesla, so famous guy. I mean, 1887, he developed the first AC motor, really marvelous. Without him, we don't have so many electromagnetic. So thanks to him. So Tesla is so famous guy, you ought to know about him. 1887, even though our vehicle EV Tesla named after him, Tesla, first AC industrial motor. And then since then, his work has been patented, and then let's go to Westinghouse. Westinghouse is really famous enterprise during that time, really famous to work on all the electromagnetic distribution. And then we can say that the industrial motor, the first invention for industrial motor should go to Tesla, 1887. Interesting. Okay, I will record my things. You can review it in my lecture. But before that, you go, then we do have the mini project we need to work on. We don't have lab, but we have mini project. Then you can later on review my lecture, you see what it is. And then you have to choose a mini project. But you don't present it now, present after midterm. Okay. Okay, that's all. That's okay. And then you can see that the major application of motor, of course, it goes to the EV, electric vehicle. The electric vehicle, I think, as you all know, that it went actually 180 years ago, many, many years. So that means EV is not invented last 10 years, 20 years. It's been invented nearly 200 years. Same time, right after we invent the motor. And so both EV and combustion engine are coexist about 100 years ago. It's quite interesting. I think you all know that history. But however, EV, because mainly depend on motor, depend on battery, it lose the competition at that time. IC become the dominant market for the last 100 years. So I think since 100 years ago, we have coexist between these two things. But however, EV lose the market. And then, of course, EV mainly driven by motor and also the battery. Today, we also see some of the development, the hybrid vehicle are mixing with the motor and the ICE together. So here will be one of the picture. I think I showed some of you before. Is 1832, one of the first invention of the electric vehicle in Scotland, Aberdeen. And the good thing of this motor is still the same, quiet, battery powered, but during that time, the steering is not very good. They don't develop any Ackerman steering or differential speed steering yet. And there's also famous photo you can see in many literature about Thomas Parker developed one of the can be first electric vehicle in Wolverhampton in near the London in 1884. And then you can see that fundamentally you can see the difference between the two, the motor against the ICE engine. Both of them are do energy input and rotational output in that time. Both of course based on DC energy, battery, and grid power or fuel cell to power it. Go for the electromechanism to do the job. Gasoline engine mainly about chemical system. So one based on electromagnetic, the other one are based on internal combustion engine. So that's the basic principle of them. But having said that, you can see that the efficiency will be quite different between these two. So that's why we have to use electrical motor. Firstly, engine. See, diesel engine, the efficiency is not very good. Maybe typically 15%, maybe vary from 10 to 20, but typically 15, really low efficiency. Not environmental friendly, emission, noisy. The torque profile is not really good. We can't control the torque really well. The zero speed torque, or called the stationary torque, is not very good. When the vehicle starts from standstill, the torque is really poor. We can't control them well. And we have difficult to maintain a wide range linear torque. So that means to use them for electric vehicles is not very good. We're still using them for automotive environment, but you can see that when two vehicles stand by in the traffic light, once it turns green, then the EV will go first because the instant torque for EV is marvelous. The motor efficiency is 90%. High performance, at least 95%. And then control is good. We can able to control the torque and speed really well without any emission, clean and no noise. So here will be typical comparison. You can see how we compare DC motor and AC motor. So these are two most important equipment in all the motion control system. So the power input for DC, basically we call it DC motor mean input is DC, and AC mean input are AC. DC motor, basically we have been using commutator, carbon brush to program them. So that's why it's really dirty, don't have really good nighttime, but AC using induction principle, we don't have any commutator. And so that's why they make them two major difference. So that's why people prefer AC motor more because of the safety, no contact, no brushes. And however, the control is different. DC motor is really simple, very easy to control. We can control the torque, we can just using voltage control, really simple. But for AC motor, we can't use voltage control. We cannot program the voltage and frequency so easily, so the control circuitry is more complicated. Although we say complicated, but today when we have power electronic, even how complicated we can able to program them in power electronic, but we need a power E circuit to drive them anyway. So this technique, we call it the variable frequency drive, or we also call VSD, variable speed drive. And for maintenance, of course, pure DC motor, we do have maintenance issue because commutator and carbon brush, but AC motor, we don't have too much maintenance. AC motor, when we use in the market, sometimes you can see 10-year, 20-year, 30-year motor without too much maintenance. They only use bearing, we have no oil, no lubrication. They can have a really long nighttime. For application, then we do prefer to go for the carbon brushless one. But conventionally, the brushless DC motor still have a really large market. I think it could account for 20%, maybe 30% of market still, quite a big market. It's been used for some simple equipment, toys, or some low-cost equipment. And for automotive, then we are not this kind of brushless motor can be used for window, windscreen, or seat and mirror. So that's why I can see there's many motors inside vehicle. Many factory, we have the converter system. They do need really good speed control. This motor really good in speed control, torque control. So, and also in this application as well, in computer system, we will use hard disk drive, but sometimes we convert into brushless DC too. So brushless DC is same as DC motor, but we use another principle called the brushless to do that. Once we do that, we need to use power electronic to control the motor. Instead using carbon brush and commutator, we replace them by electronic. So in this case, we don't use the mechanical contact point, we use power electronic to replace them. So because of this one, we do have really high performance. I think the market at least 30% share for DC brushless motor. All the drone and all the flying vehicle, electric vehicle, robot are mainly to use DC brushless, mainly because high performance. So that's how it's going to happen. Even though medical electronic, we try to rely on DC brushless. So AC industrial motor is still really big market. I think it counts for really 50% of the whole machine market. Mainly all the pump, compressor, all these building equipment basically are using AC industrial motor. Home equipment, like in here, washing machine, dishwasher, refrigerator, pump system, using that one. So that's why even the AC, air conditioning system, the home with the AC, we all using this industrial motor compressor. So fans, all the fans here, cooling fan are also using this one. So really common. So lastly, we need to show you motor has been already exist many years ago. This picture taken in New York roughly 100 years ago. During that time, for the whole New York, we got 1/3 of vehicle are electric, 2/3 are ICE. So it's quite interesting. Electric vehicle has been there for many years, but you just lose the market. And Henry Ford, at that time, he developed the first electric vehicle factory to make the electric vehicle in that time. And then EV is not new. Actually, even though in the Apollo program, 15, 16, 17, we launched the program, we carried the EV to the lunar surface. So all these vehicles are electric. So the weight is 210 kilograms, the speed is quite low, and the motor only 190 watt of power. That they are using less battery during that time. So here you can see that quick revision of the EV development. You can see that the first will be 1801 and a power battery. So you can see that during that time, acid battery already there. So that's why we can less battery to get a motor. We can able to develop the electric vehicle during the time. And then, as I say, the first electric vehicle being powered will be Robert Davidson. And then during that time, the first ICE also developed 1885. So these two become a big competition. And then this kind of ICE gradually replace the EV. So in here again, about 1 century ago, any cell was 4,200. You see the EV will be 38% during that time, and ICE only 22%. So you can see during that time, EV was really famous, really popular. But of course, eventually be overtaken by ICE. But now then EV come back again. So here this chart show you all the different type of the motor available nowadays. So they give you different type motor, including the DC motor, we have RAM motor and PM motor. We also have the carbon brushless, including induction motor. That's the one we focus more on. We also many other type of motor. And so all this, we'll go through them really briefly. We won't go through them in detail because mainly induction motor is the key thing we try to learn here. And also DC motor, brushless DC motor is also important. We go to spend some time. We'll try to learn some reluctance motor, also really famous motor, really important motor. But having said that, we like to show you about air gap. Air gap is one of the important elements for inductor because we cannot design inductor, a transformer, or motor without air gap. You see a motor between the stator and rotor. They cannot touch each other. Between them, there must be an air gap. Most of motor, the air gap will be something like 1 mm, 0.5 mm, depending on the motor design. So that's why to study motor or study transformer inductor, we also need to study how an air gap look like, why we need to use air gap. So that's why in here, I show you some equation formulation, what air gap is. So when we apply voltage to a transformer, then we see the magnetic flux will also increase. But however, when the magnetic flux increase, it comes to a stage of saturation. Like the BH loop I showed you, we go to the top, there was saturation. That's not really good for inductor or motor. When saturate, firstly, the magnetization will lose, and then the inductor will drop, and the motor will not have sufficient magnetization to operate. And you're getting hot. So we don't like that. So that's why somehow we do need to put air gap to prevent the motor or transformer saturation. So that's how it's going to happen. So, and if a transformer, the voltage will drop, conversion will drop, really get really hot, inductance decrease. That's all the phenomenon happen. So air gap is typical method we control the electromagnetic flux. It more look like additional resistance to control the magnetic flux. And then for power application, a small gap will be needed, usually not really big, 1 mm, less than 1. And for many motor applications, we do need the air gap because of all the things I mentioned just now, including they cannot physically touch each other. They must separate. For safety reasons, other they will just car collision. So a small air gap will be important to decide, but how small is small? That's something also quite important. We like to have really small so that we can able to increase the magnetization. But too small, if alignment is not really good, they will collide each other. So that's why that's quite important design. So here we base the equation for reluctance. Once you have air gap, then we create the reluctance. Even though iron itself, we do have the reluctance. Like in here, reluctance. If you gap the core, the core itself have reluctance. The air gap also have reluctance. The formulation of them will be like that. That relate to length for that path, the magnetic flux passing through, relate to its area, relate to its permeability. Of course, for air gap, we don't have air, we don't have mu r, right? Become mu r equal to 1, then become only mu naught in here. So that is the basic equation for reluctance. This equation very similar to resistor. Resistor is rho L over A, right? They are really similar pattern. So the longer it is, then the reluctance higher. If the area getting larger, the reluctance becomes smaller. So that's logical, very similar to resistance. So the purpose on the air gap, of course, is really essential. Also making a motor or transformer will not saturate easily. You see today the motor will be driven by AC or DC, whatever. If an AC industrial motor, then it's driven by some power electronic circuitry. So the power electronic circuitry will try to create a waveform related to an AC. So we're driving this waveform to them. If it consists some DC component, the motor will saturate. So why is that? Because DC will accumulate the magnetic flux there. Gradually, they increase, the DC flux becomes saturation. That's no good for the motor. So by using air gap, actually we can create a reluctance to stop the DC bias. So that's why the motor can become much safer. They don't saturate so easily. Because when we create the waveform by using computer, we never can make the waveform 100% symmetrical. So that's why we put an air gap will be good to eliminate the DC saturation. So that can also allow, given the higher H field, the motor will be safer. So to summarize with what we're trying to say here, then you can see that our motor will be basically a conversion from one energy, one power level to another power level. So including electrical to electrical, mechanical, electrical. So many different kinds of scenarios. Application mainly for EV, robot were the two big topics. So I think for the next 10 to 20 years, then motor become getting more and more important, mainly because EV and robot. And so, of course, motor is a key element for electric vehicle. And key thing is efficiency is so good, 95%. And we can able to provide really precise control. You can see that we can drive an electric vehicle. We need to control the vehicle, how to do steering, overtaking, stop anywhere, autonomous vehicle driving. For vehicle, you see we got two wheels. Each of wheel controlled by different motor. So two wheels need to synchronize really well so the vehicle can go straight line. And also turning proper angle. Without this one, then our vehicle cannot be a vehicle. So that is to say we need to have really precise control for angle, speed, and position. So that's the important part. Zero emission will be also wonderful. For robot, of course, we also need to precise control for robot. In the future, this are not the robotic revolution. Because for next 10 to 20 years, all our environment will be with robot. We do need to have a precise control for the robot. When you see the YouTube film, you can see that robotic control is important. Each muscle for the robot need to be controlled. The arm, the limb movement, how to move, we need precise control. So that's robotic control. We need to have good motor to do that. Good control for linear motor, rotation motor, and 3D motor. Even though all these fine vehicle ethos and also room, we also need to have a motor control. Not only said that, the next revolution for transportation will go to electricial. We have been doing really well for electric car, but next item we need to work on will be for marine application, how to control all the vehicles. You see, in an electric vessel, we not only control the propeller, we need to control the ship movement, turning, steering. So that's also the future motor drive we need to work on. So that's why so much work now we need to start to work on motor. I think motor has been really ignored by many electrical engineering. If you go to all the university in the United States, they don't have any good program for electrical machine because their professor don't care about it. They only focus on data analytics and AI, but without motor, nothing can happen. Without motor, there's no robot, no EV, no transportation, no power generation. So the final remark will be, electrical machine is a core component for us because it relay, connect electrical and mechanical together. The future is electric. Everything will be powered by electrical means. I don't think there's any other energy source better than electricity. So in this case, all the things related to EV, robot, renewable energy are all highly depend on motor and generator. Motor and generator exactly the same item. So that means today we lay out the foundation, how to understand robot. That can be one of the future design for all the transformer generator. So absolutely, that will be an important growing field. We need a lot more of the engineer in this area. So if you want to understand more, so that's more detail. I don't have any textbook because textbook, I can have textbook in my syllabus. If you go to my syllabus, I go find four textbook, but they're really expensive, $300 each. If you like, you can buy it. If you don't like, focus on my lecture notes and also my hyperlink here, then you can know all the details. So before we go away, then let me stop. Then we just go through quickly about our syllabus. So our syllabus here, then you can see that the other are basic stuff. So we got to have a textbook here. If you like, you can get one from the library or from the Amazon, but they're really expensive. $300 each. I don't recommend you to buy it. And then our course divided into here. Then we have the, I want to record it, so that means I like to share it so that you know what I'm talking about. So we do have homework and quizzes and midterm and final exam and project. The project is something I like to spend more time with you later on. And for our course, then we will have this kind of the initial schedule. Then you can see what's going to happen. You do have some homework assignment here, as usual, midterm, and then quiz 1 and quiz 2. So that's all the assignment we need to do. And important thing will be the project. We don't have time to go through all the project. I just start to look into the project so that you know what we are talking about. We don't have lab here, but we like you to look into the project. I will discuss more detail of the project next week. So let me share them. Then I can share it because I want to record it in case you want to review what we discussed. So we don't have labs. However, we do require you to choose one project from my list here. So there's a many topic here. I will go for each of the topic briefly. So basically, you have this 11 project and then conduct it throughout the whole semester. And then you can present it. So that means what you need to do will be, the deadline roughly about in the end of December. Then this individual project, one student, one project. And then you need to submit the project report to me plus a presentation, PowerPoint presentation, like any other project. But that's a mini project. I don't require you to do also a lot of things. It's just, you can see that from the syllabus, we have total 6 hours. So 4 hours will be roughly about a lecture, 3-hour lecture. The other hours will be the project. You spend your own time to work on the project. You can come to my lab, research lab, to do your project if you like, if they're hardware. But if you choose software project, then you can do it anywhere. So of course, in the present, after the midterm, you can start to book a time for a presentation in the class. So each class, then we have, say, you can present 50 minutes to present what you have learned from your own mini project. So there's about more than 10 projects. You can select any one of them. I do encourage you to select different topic. But of course, if you think this topic interests to a few of you, you can still select the same. And you need to present with some PowerPoint. And you can also present a hardware project. You can bring to the desk here to present your hardware in front of us. Then we can all learn from you. So the project report, we don't need too many pages. About 8 pages will be good enough. But if only a survey or desktop study without any hardware, I prefer more pages, maybe 12 pages. And then the presentation will start from week number 8. So do start to book a time. Later on, I will prepare a Google Share folder so that you can fill in your name to book a time. So if you do hardware, come to my lab. So you can see that here are many projects here, including build motor, and also to control an inverter output using microprocessor. If you know any Arduino and Raspberry Pi, then you can try that. And I think you all know how to do that. And computer simulation using MATLAB, Python, study EMI, dynamometer, and also program electric using web programming, and develop inverter drive, DC motor drive system, and also machine system, and also using Python simulation platform, and thermal modeling, how to develop thermal model, and also literature survey for some new machine technology. So there's a number of projects. You choose anyone. They all have different kind of the topic. And also write down the requirement from me, what deliverable is needed. So go through them at home. I think next week we'll also discuss them more detail so that you know my requirement. Any question? Okay, good. I hope you enjoy my lecture, enjoy the motor stuff. I think motor really, really important. And it's a big thing. It can be really good research topic anyway. So I will see you again next week.